Okay, great. So account abstraction has been one of the big ideas that has been making a lot of progress within the Ethereum ecosystem lately. So who here has heard of account abstraction? Who here has heard of a particular wallet that's implementing account abstraction? Who here is building one of those wallets? Who here is building an L2 that's looking into supporting it? Okay, so a lot of good work on account abstractions already happening. So today what I wanted to go through is the history of the concept, basically from the beginning of Ethereum up until the protocols and some of the challenges that we have today. So before the launch of Ethereum, when Ethereum was just being conceived and the protocol being specified for the first time, one of the big ideas that we settled on is this idea that in Ethereum you're going to have two types of accounts. There's an account that's called an externally owned account, which is an account that you can send transactions from if you have the private key for that account, right? So if anyone's using a kind of regular Ethereum wallet today, you're probably using an externally owned account. And the second type of account is what's called a smart contract account. A smart contract account, instead of being controlled by a person, someone who holds a private key, is controlled by a piece of code, right? So this is like the big thing that Ethereum has that blockchains before it did not really have, right? Which is that you have these contracts, and these contracts have the ability to have their own internal storage. They can hold ETH, they can hold assets, they can make actions, they can send like some of their ETH, they can talk to other contracts, call functions of other contracts, and this is all what makes Ethereum cool, right? Now, there's in Bitcoin, there is also a scripting language. Now, it's a very weak scripting language, and it's very difficult to use it for all but the simplest applications, such as multisig, right? But it exists. So in Bitcoin, instead of having like accounts that can take multiple actions, you have UTXOs, which are basically like one-time accounts, right? When you have coins that are in a UTXO, if you send a transaction that spends that UTXO, you're spending the UTXO completely. It does not exist anymore. And if you want to keep some of your money, then you have to put it into a completely new UTXO. So there is a script, and what the script handles is it handles verification, right? So as part of a transaction, there is an input field that's called a signature, and this function is able to go over the signature and over the hash of the transaction, and it's able to determine whether or not the signature is valid, and so whether or not it can spend the money. In Ethereum, the script was also used for execution, right? So you can make or code of a contract account can make that account do different things. It can make it send partial balances, so if it has 100 ETH, it can send 30 ETH, or it can send 5.9 ETH. Can't send 120 ETH, but maybe it can send 80. You can store and load to storage, so every account has its own like mini virtual hard drive that it can read and write from. And it can talk to other accounts and call functions of other accounts. Now, in Ethereum, the script which is called the EVM, is used for the execution part of an Ethereum transaction. It's not used for the verification part. For the verification part, there is kind of one fixed algorithm that EOAs have to use, which is ECDSA signatures, right? These 65-byte signatures, you have your R value, your S value, 1 bit for the V. If you've done your coding, you've seen these before. And it's like one exact signature scheme that gets used to verify whether or not a transaction actually was signed by a particular account. Now, why did we restrict verification to just being ECDSA signatures instead of letting the verification part of a transaction, the part that determines whether or not the transaction can even be included on chain, depend only on ECDSA signatures. Probably the biggest reason was that Ethereum transactions can contain much more computation than Bitcoin transactions, right? Now, in the extreme case, this is actually not true in Bitcoin, right? Because in the extreme case, you can make very big transactions, and there was this quadratic vulnerability by which you could actually make a transaction that has like hundreds of different inputs, each of which require hashing over the entire transaction, and so you actually have to hash and square data, and it actually gets pretty annoying. But like in practice, big parts of the script are disabled, and there are kind of standard transaction rules that make it very difficult to send those kinds of transactions. The total capacity of the system is very low, right? But if you compare Ethereum, well, at launch, we had pi million gas per block, right? 3141592 gas per block. And you could do a lot in 3 million gas. And so you could basically just, if it was possible to make a transaction where the process of verifying whether or not it's allowed to include that transaction on chain could involve huge amounts of Ethereum gas, then people could send transactions that require huge amounts of computation to verify, and a miner would not be able to know whether or not they could even include those transactions without spending a large amount of computation, right? So in the Ethereum context, requiring miners to verify these transactions fully before maybe getting paid, or maybe if it's a DOS attack, not getting paid, is just not reasonable. So one piece of thinking in early 2015 that we had is, like, I've been a fan of multisig for a long time, right? Back in 2013, I wrote an article for Bitcoin Magazine talking about how multisig is the future of Bitcoin. Back in, I believe 2012, I wrote an article just listing examples of people's accounts getting hacked and people losing their accounts that just showed, you know, how bad the security of single key accounts is and how we desperately need to switch over to something better. And so for a short time, there was actually a dream of basically launching Ethereum in such a way that the average user would actually have a multisig wallet that they would hold their coins in, and this is what people would use straight from the beginning, right? Now, of course, as people involved in account abstraction know today, doing that would have required people to keep some portion of their ETH separately in an EOA, because only EOAs, externally owned accounts, are allowed to actually initiate transactions, but like, that's fine, we can write software to manage it. Now, the problem is, there just like wasn't enough time, right? At the time, the Ethereum community was breathing down our necks, desperate for Ethereum to finally launch after 1.5 years of delays, and so we just cut a huge number of features and we just said, boop, boop, ship it! And so Ethereum was shipped. So, one unfortunate consequence of this is that the over-optimism that we had on everyone using multisigs actually ended up backfiring, right? So this was some interesting historic trivia. Basically, in Ethereum, there's this opcode called a log, right? And when you make a log, then that registers data in a separate tree. It does not get saved to storage where it can be accessed later. It just gets saved to a separate tree where it gets kind of published and then ignored. And nodes would be able to read these logs, and this would be the way that applications would communicate information about events that happen on-chain to their users. Now, one thing that we never did is we never automatically logged ETH transfers, right? We made sure the multisig wallets log ETH transfers, and we made sure the ERC20 tokens log ETH transfers, but EOAs by themselves never did. The reason why is probably because, well, it was because we expected users to switch over to using multisigs, and we even wanted to like create an extra push for users to use multisigs. And multisigs would log everything, and everyone would read logs. The problem is almost nobody used multisigs, and so exchanges, when they were checking for ETH deposits, they would check transactions. Like they would go through the transactions, they would find the sender, they would find the recipient, but they would not check logs. And so, as a result, multisigs actually had a harder time getting their deposits seen by exchanges for quite a long time than EOAs did, and this actually would have hampered multisig adoption even more, right? So a bit of a early screw up and tragedy, but you know, fortunately since then things have improved. 2016, this was the first attempt at what we call account abstraction. This is EIP 86, which is outdated. You're supposed to see 208 for current details. Unfortunately, this thing is so outdated that even 208, I believe, doesn't actually mention that 208 is also outdated by now. But oh well. So what this thing basically does is it says, if the signature of a transaction is 000, then treat it as this transaction that's a totally different object that is set where the sender address becomes sent to this like entry point address that nobody controls, and then it just becomes a piece of data that gets sent to an account. And then if you want to do a creation contract transaction, then basically we add a way to create accounts that have a specific piece of code where you know the address of a particular contract before you could even publish it, right? This is like one of those sort of subtle problems in account abstraction. Basically, like one really big key property that we want blockchains to have is we want it to be possible to give you money before you're registered, right? Because in order to register, you have to pay fees, and in order to pay fees, you need money, yes. You're supposed to maintain the parallelism in the sentence, and the ETH is money meme was like years old. Apparently, we're like ultrasounds, and like maybe we'll be like, I don't know, like Negasound or something. But yeah, basically, it's like if you don't have money, you can't register, and so you need to be able to have an address that you can use to receive money before you're registered, right? So the basically, what that requires is the ability to be able to make a piece of code that contains verification logic where you can, just given that piece of code, you can calculate what the address will be when that contract later gets published on chain. And you can be guaranteed that nothing else can take that spot, right? So the default contract creation mechanism does not do that. But this mechanism where the address is the SHA-3 of the code, that ends up doing it, right? So if we do that, then basically you're able to create a piece of code that determines how transactions are verified, then hash that, generate the address based on that, give the address to your friend sends you some ETH, the ETH goes into an account that does not yet exist, and then you can send a transaction that actually basically uses that ETH as a transaction fee in order to initiate that account. Now, that second part we actually did not yet figure out in EIP 86, right? That actually would take at least a year before we realized properly that that's necessary. But the core idea is basically like you have these transactions where the kind of top level address is this kind of common entry point. In this case, we use 2 to the 160 minus 1, which would be 0xFFFFFFFFF. Basically all the transactions would start there, and then that would be a call to what your actual wallet is, and then your wallet would have logic so that your wallet can make other calls. Now, the big challenge with account abstraction is miner strategy, right? So the problem that I talked about at the very start of this presentation, basically, if you are a miner and you receive a transaction, how can you get a guarantee that you are going to be paid for the transaction without running through potentially hundreds of thousands or even millions of gas and maybe getting an answer that you're actually not getting paid at the end and having wasted a whole bunch of computation? Now, one simple approach, whitelist a set of code hashes, right? So that way we could just like start off by introducing some basic known types of accounts. Another option is having a mechanism where you could have a template for an account where if an account follows an account's code follows that template, the template guarantees that the miner will be paid early on, and there's no way later on to make that payment get canceled or reverted. Right, so the way this basically generally works is you have 3 calls. The first call is, well, before the 3 calls, you do signature and nonce verification. Then you will increment the nonce. Then the first call is to basically pay the miner. Then the second call is a call to self. And then inside that call to self, you do whatever you actually wanted to do. And the reason why it's a call to self is so that if something fails within that call to self, the kind of inner call can revert, but the outer call doesn't revert, and so the payment doesn't revert. And then the third call would then basically call a contract and get back the refund for whatever gas you did not use, right? So you have this template, and any contracts that follows the template is guaranteed to pay the miner. A third strategy is to just say we're going to restrict account abstraction to transactions that require less than, for example, 250,000 gas. Anything that requires more has to be sent through EOAs for now, and maybe in the future we'll figure out some other way, or maybe in the future we'll just convince all the Ethereum users to not require more than 250,000 gas, except for anything but like maybe contract creation. So that was the early thinking. So problems with early account abstraction. As we mentioned, if you're a new user, you don't yet have coins, you'd have to find an existing user to create an account for you. Problem one. Problem two requires complex logic inside the accounts to handle paying the miner, getting a gas refund, all of these complicated things, which requires like this complicated template that I just described. Third problem, transaction hashes are not necessarily unique, right? So in Ethereum, transaction hashes are unique because a transaction hash depends on the signature, it depends on the nonce. The nonce increments every time an account sends a transaction. And so there's just no mathematically possible way to create two transactions that have the same contents, that have the same hash. With account abstraction, you can make an account that does not have that property, right? Like you can make an account where the nonce automatically resets every 24 hours. And if you do that, then ta-da, if you send one transaction, you could send that exact same transaction 1 day later, get it included, and hashes are not unique, and Etherscan and Etherchain break, right? Now, and maybe the Geth API will have to be totally redesigned to return a set of transactions instead of one transaction. So, I mean, that stuff is all theoretically manageable, but it's like a pretty large amount of overhead, right? It's actually, even the current ERC-4337 proposal ended up like forcing a particular nonce system to make sure the transaction hashes are unique. One big and very subtle problem with early account abstraction is what I call the multi-invalidation issue, right? The multi-invalidation issue is basically that if you have a piece of arbitrary EVM code that's verifying whether or not a transaction is valid, then that EVM code could go access other accounts. And then what if you create a structure where you have a whole bunch of accounts and a whole bunch of transactions, and they all access the exact same account, and like let's say they just check some particular flag in that account whether or not it's true, right? And then so first you do a bunch of computation, as much computation as you're allowed to do, then you go check the flag, and then if the flag is 0, then it passes. Now, let's imagine that someone creates 1,000 of these accounts and then publishes into the mempool 1,000 of these transactions. All 1,000 transactions, if the value in the storage over here on the left of this flag is set to 0, all 1,000 of the transactions are valid, right? But there is a problem. Only one of them can get included. And once only one of them gets included, the flag changes to 1, and then all of the other transactions are invalidated, right? And so the problem is you can make an arbitrarily large number of transactions, pollute the mempool with those transactions, make miners do a huge amount of work verifying them, and then you just like take the simplest transaction, let it get in, send it with the highest gas price. You know, maybe the simplest transaction would not even do the 2 million gas of computation, it would just poke straight into the S. And then it would just set this flag over to 1, and then this like really huge amount of stuff gets invalidated, and so you never actually pay the fees for it, right? And so this creates a very cheap DOS opportunity. So this is like the big problem that is responsible for like probably half the complexity of modern account abstraction schemes. So moving forward a bit, some proposals from the 2017 era. Proposal 1, remove the nonce abstraction. Basically, do the rest of account abstraction, but require the transaction to still use the existing nonce field, require the nonce to be increased by 1 by the protocol, and so by doing that, you remove people's ability to do their own nonce logic, and so remove the ability for people to make duplicate hashes if they want to, right? Standard. Second idea, standardize the signature scheme, right? So basically, transactions would have a dedicated field called a signature, and then the transactions, in the top level message, the transaction, or the call data that you get, or in this case, the return data, it would include the signature and it would include the signature hash. And basically, this kind of grabs up a lot of logic that would otherwise have to be in the contract, and it sort of standardizes it for you, and it lets you just make the verification account itself much simpler. A breakpoint opcode, right? So the idea of a breakpoint opcode is basically that if a transaction does an exception after the breakpoint, it doesn't revert all the way, it only reverts back to the breakpoint and then it stops there. And the idea there is that you would split your account logic into two parts, verification part, execution part. After the verification part, at the end, you pay the miner, and then right after paying the miner, there's a breakpoint. And so if something breaks, it only reverts back to the breakpoint, and so no matter what happens later on, the miner still gets paid. Now, the problem is this is a pretty big change to the EVM, and especially at this time, client teams were pretty allergic to changing the EVM. So this ended up not happening. A bunch of other proposals ended up happening. There was this interesting one called the pay gas opcode, which basically kind of pays for gas that automatically gets refunded. And so the entire gas refund mechanism ends up being handled by the protocol instead of being handled by the account. There's a panic opcode that could be used to invalidate the transaction before a breakpoint. There's a bunch of different miscellaneous ideas. There's a proposal where a transaction can include a piece of salt and a piece of code, and so you can actually create an account abstracted account at the same time as sending the first transaction from it. So there are a bunch of different ideas that we were grappling with. I think probably the most challenging trade-off that all of these systems were trying to handle is this question of like how much to enshrine versus how much to leave to the user, right? I think early account abstraction had this big dream where the dream was that we would reduce the transaction logic such that a transaction and a call are the exact same thing, right? A transaction just equals one call, and then everything that's required user level for verification or whatever, that happens inside the EVM, right? So basically trying to create this like really lean and clean system where the logic that's needed for verification is itself all done by the user and everything is done with contract code, and Ethereum can be like this really clean and minimal system that specifies basically nothing. Over time, we ended up moving further and further away from that model, right? So we've, we became willing to enshrine nonces. We became willing to enshrine certain things about fee payment. In the ERC 433.7 proposal, there's actually now a medium-term desire to enshrine ERC 433.7, and then accounts would all have to go through the ERC 433.7 entry point. And so there's this thing that makes basically a whole set of verification calls and then a whole set of execution calls, and accounts have to have both of those. And then there's the desire to have in-protocol censorship resistance mechanisms like inclusion lists, and inclusion lists would also be aware of the concept of transactions but not the concept of calls. And so we're actually moving in the direction of enshrining more because that's better for user security. But at the very beginning, the philosophy was the opposite, right? And like trying to preserve as much of that simplicity as possible was a big part of the motivator that kind of resisted adding some of these extensions. So primary goals here, handling account creation, what happens when you're using an account for the first time and the code is not yet on chain, making sure that you can put the code on chain as part of your first transaction. Verification complexity, basically trying to make sure that the accounts that do the verifying can be simpler if possible, and issues around hash non-uniqueness, basically not making life hell for the Geth API or for Etherscan, but we were not yet thinking about the multi-invalidation problem. So, ta-da, 2018. Who here remembers 2018? Who here was happy in 2018? Who here was less happy in 2018? 2018, it's a good year, I remember prices dropped, right? Like, at the end of the day, isn't that what matters, right? Maybe if, prices are so important, right? Maybe like if we get the price to like under 100, then like, that'll be awesome. Okay. So, verification time access restriction. This is what 2018 was actually good for. And basically, the idea here is that during the verification step of an account, or of a transaction verification, there would be a restriction by which that code execution is not allowed to read or write the state of things outside of that account, right? And so that whole mechanism I showed you a few slides ago, where you'd have 1,000 accounts, and those 1,000 accounts would all read this object called S, and then you could send one transaction to invalidate that object or to change that object state, and then suddenly 1,000 transactions are invalid. That would not be possible anymore, right? There would be a hard invariance that the only thing that could invalidate a transaction from account A that looks valid today is itself if account A has either that transaction or a different transaction included, right? So multi-invalidation would not be possible anymore. And so you would have basically the same kinds of invariants and like security properties in the mempool that you have today, and so the whole thing would be much more secure against denial of service. And this is something that would be verified by miners, right? So basically, like miners would have their EVM logic instrumented in such a way that if they're verifying an individual transaction for the purpose of determining whether or not it's okay to include or whether or not it's okay to forward, they would run the EVM with a special flag, and that flag basically says, okay, if during the pre-pay gas portion, during the verification portion of a transaction execution, if it hits if it reverts or if it hits some opcode that triggers a failure, then that entire transaction gets thrown out, right? So this actually plugged the biggest remaining hole, and it was a good idea. But the problem is that, as you can see, there's like an entire 2-year jump between 2018 and 2020. Who here remembers what happened between 2018 and 2020? Okay, nobody remembers Uniswap? Okay, but aside from Uniswap, the biggest thing that happened within those 2 years is basically the Ethereum proof-of-stake research kind of ecosystem really kicked into full speed, right? At the beginning of 2018, we announced that, like, hey, we would love to have some consensus client teams implement the proof-of-stake side of Ethereum, and we roughly know what proof-of-stake is going to look like. And then, we have that big workshop in Taipei, then we had that workshop in Berlin, and then we had more workshops, and at some point, actual code started getting written. But during this time, developers were very busy, and we definitely did not want the execution developers, so the Geth people at the time, the parity people, starting to be Netherminds people, all of these wonderful groups, to have any extra stress at a time when they were already busy with maintaining the client and possibly preparing for having to make the biggest change that Ethereum made in its lifetime, which would be switching to proof of stake. So 2 years later, 2020, EIP 2938, right? This is a concrete proposal that includes all of the different pieces of account abstraction ideas that we had come up with in the years previously, and finally, for the first time, puts them together into a single package that actually is an EIP, and so it's actually formal enough that you can go and actually implement it. So the pros are it solves the problems. The cons are that it's very complex at the protocol layer. Devs were still working hard on the merge, and so it also ended up not being implemented, right? But it was progress because it shows that, hey, we have a concrete idea. Independently built account abstraction alternatives, right? So the Ethereum Foundation is far from the only group that cares about the problems that I talk about. And there's other groups that also cared, and there's even other groups that had their own problems that they cared about that later on ended up kind of getting merged into the account abstraction umbrella and ended up getting handled by the proposals that we see today, right? So gas station network. So basically, this is a system where you could make an off-chain message. So you could just make a message, pile of data, including a signature, whatever, and you can pay someone to wrap the message in a transaction and include that transaction on-chain, right? So if, for example, you have a Gnosis Safe wallet, who here has a Gnosis Safe wallet? Okay, cool. Who here has an EOA? Wait, more people have Gnosis Safe wallets than EOAs? This sounds wrong. Do you guys like share EOAs to like use your Gnosis Safes? Okay. So basically, yeah, if you have a Gnosis Safe wallet, right, then to send a transaction from that Gnosis Safe wallet, you have to like go call the, the execute function, right? And to call it, you need to make a call, but then a call by itself cannot go into the EVM, only a transaction can go into the EVM, and so using the gas station network, you would be able to pay someone else to actually make that transaction that then includes a call that goes to your safe and lets you take some money out. And the payment could even happen from your Gnosis safe, right? So it solves the problem, it makes it nice. The problem with this approach is that it requires every single operation to be wrapped in a separate transaction, right? And that adds an extra 21,000 gas per transaction overhead, which is not very nice, right? So then there was also the Argent wallet. They were, amazing group working on social recovery before social recovery was cool. They also used smart contract wallets, and so they had very similar problems, and so they implement something very similar. There is also a new goal that was being introduced, which is this goal of letting people pay fees with ERC20 tokens, or more rarely, sometimes letting application developers pay fees for their users, right? So if you imagine you want to make a wallet that's targeting users in Latin America, and users in Latin America at the time do not deeply understand cryptocurrency, and so you want to make the user experience simpler, and you want them when they receive USDC to be able to send that USDC. The problem is, if you just use Ethereum directly, if you receive 10 USDC and you receive nothing else, you don't have any ETH to pay for gas. You have no way to spend that USDC, right? And so what you'd want is a system where people actually could use the USDC to pay a third party, and then the third party includes the transaction and the ETH gets paid, right? So this is a sort of thing that can also be built using these kinds of wrapper mechanisms, right? Also, if you want applications to be able to pay fees for their users, also use wrapper mechanisms. But the problem in all of this is that every single operation requires a separate transaction wrapper. That's an extra 21,000 gas, and so it's pretty high overhead. EIP 3074 is a lovely proposal by Sam Wilson, Ansgar Dietrichs, Max Garded, and Micah Zolto that basically targeted some problems that ended up going under the account abstraction umbrella, but that were somewhat different from the account abstraction concerns that I had, which is that I want everyone to move to multi-sig wallets and be able to use multi-sig wallets super easily and cheaply, right? So, and also one of my other goals, by the way, is when quantum computers come, I want people to be able to upgrade their existing accounts to quantum safe cryptography and without us having to be opinionated about which quantum safe algorithm you use, right? So, there's a lot of things in there. So sponsored transactions, including, so the ability to use USDC to pay for gas if all you have is USDC was a goal. Being able to make multiple actions per transaction. This is like a really important goal for user experience purposes, right? Like, who here remembers the experience where you have to, like on Uniswap, if you want to convert USDC to ETH or you want to convert whatever else to ETH, you have to first send a transaction to approve USDC, and then later on you have to send a second transaction to actually perform the trade so that it can at which point it can grab USDC because you've approved it. Like, who here remembers this? Okay. Who here remembers doing this back during the dark old era before the merge and before EIP 1559, when an individual transaction would often take 5 minutes to get included on chain? Okay, so a lot of problems get solved if you can just make one transaction that includes multiple calls. One transaction, first call, approve, second call, execute, easy, right? So this was, I think, a big part of the dream that also motivated EIP 3074. Modern account abstraction includes both the reasons why I've wanted account abstraction since the beginning, and it also includes these newer user experience concerns that are very valuable in some different directions, right? So 2021, a year later, ERC 4337, or EIP, yes, it's an EIP, and there's or it's an ERC, and there is a long-running technocratic debate about whether ERCs are a subset of EIPs or not. I guess right now, according to like eips.ethereum.org, they are. I mean, my preference would be for those to be two separate categories, but like whatever. Basically, 4337 tries to do the exact same thing as 2938, but instead of changing the Ethereum protocol, it all does this with layers on top without needing to make any changes to the Ethereum protocol at all. So the way that it works is it makes a contract called the entry point contract. And then the way that wallets work is wallets trust the entry point contract. So they basically give the entry point contract root access to authorize operations from their account. Now, there is an actor called a bundler, and a bundler creates a transaction that can wrap many different user operations. Right, so there's still the 21,000 gas overhead, but you only really need to pay the 21,000 gas overhead once per block. So what happens is, then there's this really interesting thing where you split up the phases, right? So first you go verify every wallet, or you go verify every transaction, and then you go execute every transaction, right? Now, why do we do this? Well, I mean, one reason is that we don't want execution to be able to interfere with verification, right? But there's actually a bunch of other reasons why it ends up being super elegant, right? But the way this works is this is all done without changing the Ethereum protocol. So they pushed out the entry point contract on chain. Wallets would individually choose to trust the entry point, and then users that have their operations would send their operations through a separate dedicated mempool, a separate peer-to-peer network, where bundlers would be able to listen to it, bundlers would be able to grab up a whole bunch of these operations, and they would include them in a block. This also ends up depending on the MEV ecosystem, right? So the ideal thing would be if a bundler just ends up being the same actor as what we call a billeter, basically those actors that like grab up the or identify transactions that contain MEV and claim MEV, and like they would also be able to run this other specialized logic for this other sub-protocol, and they would be able to create this account, right? So basically using the MEV ecosystem, at the time Flashbots, now MEV Boost, in the future in Protocol Enshrined PBS, as a way to create this open relayer market, right? So this resolves the other big criticism that I had of like the gas station network approach, which is like, hey, they're just one entity, and if there's one entity or even a small number of entities, then like they could disappear, they could be made to disappear, lots of things could happen. And so like it's not really stable to create an ecosystem of wallet users that rely on it, right? But if you have an open market, then like if one provider disappears, any other person could come in and become a provider to take their place, right? So the key innovations here are the trusted entry point mechanism, the idea of like a wrapper transaction that wraps many operations and not just one, the MEV ecosystem, and this idea of like first verifying everything, then executing everything. Now, this is all done, again, without making any modifications to the Ethereum protocol itself, and so this makes sure that Peter Szilagyi and all of the wonderful dev folks don't have to do any extra work to make ERC 4337 happen. One big extension to ERC 4337 is paymasters. Paymasters are like an extra mechanism that goes on top of ERC 4337 and is actually part of the EIP that basically allows for kind of other actors, actually smart contracts, to do things like converting USDC into ETH or verifying signatures and releasing ETH, things that can be used to allow people to do things like paying fees with USDC or use it with whatever coin they're transferring, and like allowing applications to sponsor transactions for their users. Another more recent extension is signature aggregation, right? Basically, the idea here is if there are these techniques that allow you to take many signatures from many transactions, combine them into one object, which is much smaller, and which can be much more quickly verified than verifying all of the transactions individually. And by doing so, you can save data and you can save gas. This is actually especially a big deal on rollups, because in a rollup, because a big part of the size of a transaction is a signature. On a rollup, computation is cheap, but you still have, data is, but data all still has to go on chain. And so computation becomes 100 times cheaper, data has the exact same cost, and so you have to find some way to compress data. This is a diagram I published about, I think last year in a tweet, and you see how a signature is a big part of the data, right? And so if you can get rid of the signature by replacing the signatures of all the transactions with a single aggregate, then you can actually save people a huge amount of data. And if you combine it with all the other techniques, you can get like an 8x cost decrease, or maybe 7x, which is super amazing. BLS is one very simple way of doing it. I have a post here on how to do it from a few years ago. More recently, you can also try snark aggregation, which is more generic and works with everything. So account abstraction challenges today, right? One is that the pendulum is swinging back toward enshrining more things, because enshrining is more efficient. Enshrining reduces the risk of bugs. And also, we have to enshrine if we want the censorship-resistant mechanisms like inclusion lists to be able to cover account abstracted operations in addition to regular EOA transactions. And so there's actually ideas to enshrine ERC 4337 over time. We also need an EIP to allow existing EOAs to upgrade into contracts, because lots of people don't like changing their accounts. Account abstraction on L2s. Standardization, making sure the protocol works in the same way across L2s, just like EOAs work the same way across L2s. Integration into existing technology. Including one interesting thing I heard, there's biometric signers. There's this company, I think their name, I forget, sounds like Ozempic, Alembic, right, they're doing biometric signers. And basically, you provide some biometric and then provides your key, right? So if users have multi-sig wallets, we have to actually decide what those individual multi-factors are, right? And so we need huge amounts of innovation on that too, and integration into that side of things, and finally, integration into existing wallets. But account abstraction has made a lot of progress, and I'm excited about all of the progress that it will continue making in the future. So thank you.